Let's start with a little bit of terminology. If you take a lasso and you whip it just once, that's known as an impulse, and that will result in something that looks like a single sine wave. Now, if you take that lasso and you whip it up and down multiple times, you end up getting a waveform that looks like this, and that's known as a continuous sine wave. Now, if you take two waves and you let them interact with each other, multiple outcomes can occur. For the case of constructive interference, this is a case where you have a crest interacting with another crest and they're moving towards each other. You notice that suddenly the amplitude doubles because you're adding the two waves on top of each other, and it may seem like an illusion of them bouncing off each other, but they're really not bouncing off each other. Instead, their momentum still passes through. So in other words, the wave that's moving to the right still moves to the right, and the wave that moves towards the left still moves towards the left. Whenever you combine a crest with another crest, you form something known as a supercrest, and if you have a trough interacting with another trough, then you end up getting a super trough. Well, what if you have a crest and a trough interacting with each other? You end up getting something known as destructive interference. You can see that these two waves come together and then they seem to cancel each other out. And that's because they are adding on top of each other. So a positive impulse plus a negative impulse will sum to a net value of 0. And the moment it goes to a net value of 0, it's known as a node. And that's what's being formed right here during the animation. All right. Armed with that knowledge, let's go and predict what the outcome will be when you have these two waves interact with each other. So you have this rectangular wave moving towards the right, and you have this, I guess, upside down M moving towards the left. I don't have this animated, but you can imagine that at some point the rectangle will be directly on top of the upside down M. And I'm just drawing a very brief outline because we want to see what the sum is at this point in its motion. All right. Well, for one thing, if the value is at 0, 0 plus 0 will always equal 0. So we know that both of these legs will look like that. Next, we notice that the rectangular wave has a positive value of +2, and the upside down M has a value of -2. +2 plus -2 will give you a value of 0. I'm just going to draw a big dot just to remind us that that value there will be at 0. I'm going to go to another extreme. How about right over here? All right. We see that the upside down M has a value of 0 here, and the rectangle has a value of +2. So 0 plus 2 will give you +2. And then the last part, +2 plus -2 will give you 0. So that might give us an indication of what the shape will be. And if you're having a tough time trying to guess out the rest, then just find out more points. All right. So for example, let's see what happens right over here on the grid line. We notice that the red wave has a value of +2, and the blue wave has a value of -1. 2 plus -1 equals +1. And if you're still unsure about the pattern, well, we can also take a look at a splice right through here. All right. So the red wave has a value of +2. The blue wave has a value of -1.5. 2 plus -1.5 gives you 0.5. Still having troubles trying to figure out what's going on? There's nothing wrong with splicing it even in between two known points. In this case over here, we have a value of +2 plus -1.75, which gives us a value of 0.25. And at some point, you'll figure out what the pattern is, so there is no point in adding more dots. So that's what's going to happen right over here. All right, at least in this portion of the picture, this wave plus this wave will equal that wave. And if you've guessed it out by now, congrats. You'll notice that linear relations plus linear relations will still give you a linear correlation. So really all you need to do is just find extremes on the graph and then play connect the trends. So linear plus linear will give you linear, linear plus curve will give you a curve, and a curve with a curve will give you an even more extreme curve. All right. And don't forget that there is no energy loss here. It's just that you're looking at what's happening when they're directly on top of each other. It's not like playing with, I don't know, shower water where you have two streams hitting each other, all right, where they end up losing energy. No, these are waves that can pass through space, and you're just looking at what happens when they're directly on top of each other, which is the sum or the superposition of the two waves. So this rectangular wave will still be moving towards the right. So after the interactions of these two waves, when they're on top of each other, the red wave will still move to the right, and it would look something like that. and the upside down M would be somewhere on the left of your chart paper. So your end wave would look something like that. All right. Now in your homework, there may be questions where I'll tell you that these waves are moving at 1 unit per second. So in other words, after 1 second, the rectangular wave has moved over here. After 2 seconds, it's somewhere over here now. After 3 seconds, it's moved to a point right over here. And similarly, with regards to the M, at 1 second, it would be somewhere here. And at 2 seconds, it would be somewhere around here. And so on and so forth, to a point where they will probably line up with each other if I drew this any better. All right, as a reminder one more time, when you have a wave reaching a boundary, you always end up getting an effect that looks like this. So you'll see that when the wave hits the boundary, this is a rigid boundary, causing a complete inversion in the reflection. So the reflected wave is inverted. On the other hand, if you have a free end reflection or an open end reflection, you'll notice that the incident wave will return back in phase with itself. You'll also notice something very interesting happening right over here. Let's let it animate again. You'll see the amplitude actually doubles. And that's because as the wave is traveling to the boundary, it will reflect, and when it reflects, it's at the same amplitude as its incident. So that's why the value will temporarily double at that point there. It is a small hack that's actually used to try to amplify a signal. So you let the signal transfer from a medium to a vacuum or something that behaves as a vacuum, and you'll temporarily get a double in amplitude. There is a huge catch though, and it's that you'll end up having a reflection. So the wave may echo on itself, making a very messy signal if you're trying to just signals just one way. With regards to partial reflection, it's not always going to be the case where you're going to transfer a wave from one medium to nothing, or from a slower wave, or sorry, from a medium to a dead end. All right, you may end up having a change from less to more, from more to less, and this will be the outcome. As a reminder, whenever you go from less to more, there will always be an inversion in the reflected wave, and it'll look something like that. As an aid, here's the waveform superimposed on top of the real life setup. All right. If you look carefully in this video, you'll see that on the right hand side over here, that there are these masses added on to the tines, and the masses add extra inertia to it. With the additional inertia, it takes longer for the masses to return back to their original position. And that's how Steve Mould was able to simulate changes in mediums from a faster medium to a slower medium. And hopefully you can see that in the real life video as well. You'll see the wave moves rather quickly at the beginning, and then through the more optically dense medium, or through the more the medium with more inertia, it travels a lot slower. And whenever you go from more dense to less dense, there's still a reflection, but this time around the reflection does not invert. It still remains upright. And here's the video to accompaniment that. All right, so from a slower medium to a faster medium, you can see the wave moves a lot faster now. All right, transmitted signal, the amplitude increases, the speed increases, and the wavelength stretches out, just like how we predicted in a previous episode. Refraction from grade 10 is the bending effect due to the changes in speed. What's really happening is that as the incident wave is reaching the boundary, you'll notice that one side of the wave reaches the boundary first, and the other end of the wave takes a little bit longer before it reaches the boundary. That delay in time causes the wave to apparently bend through the second medium, right? Because one end of the wave reaches the boundary sooner than the other. So this is a case of going from a faster medium to a slower medium, and this causes the wave to bend closer to this imaginary vertical line, which is called the normal. So if you recall from back in grade 10, from less to more, you bend towards the normal. And if I was able to play this animation in reverse, that will be the case of when you're going from less to more. And from less to more, you will bend away from the normal. Please don't confuse this with diffraction. Diffraction is the bending of waves through a small little opening. In fact, this explains why you can hear people carrying a conversation around a corner. Right? Because the waveform that's generated by the speaker will diffract around openings, and then you can stand over here and listen to all the juicy gossip. Another phenomenon is known as standing waves. This is when a wave doesn't seem to appear to be moving to the left or to the right. Now it actually is moving, it's just that it's constantly interacting with its incident wave, and as a result, it doesn't seem like the wave's moving. Here's an animation. Let's just let it reset. And as you can see from the animation over here, this is a fixed end reflection, which causes it to invert. So the inverted wave returns back, but the incident wave is still moving towards the right. And you can see that they're interacting on top of each other. And at some point, you can't tell where the source is coming from and where it's going towards. All right, the wave appears to be standing, and that's why they call it a standing wave. Now, these standing waves can create various different types of patterns, especially on musical instruments like a guitar. When you pluck a string at the center of the guitar, you allow the string to resonate at its fundamental frequency. So the wave is quickly moving towards the right, but when it hits the boundary, it reflects back. Now remember, this is not a single impulse wave, this is a continuous sine wave. So by the time this first part has moved to the right, it's now moving downwards. So this wave will be the lower portion. But that lower portion is also interacting with the reflected wave, and that's why it will sum up down below and it'll sum up above later on. You can also allow a string to resonate at higher orders of resonance, for example at a second harmonic. All right, in a second harmonic, it starts to look like this. I tried to simulate it last day, and in fact I have a guitar somewhere, right over there, and I'll grab it in a sec to show you. So the second harmonic can easily be accomplished on a guitar by placing your hand somewhere in the center of the string, and this coincidentally matches up with the 12th fret. So here is our reference note, and by carefully placing my finger right at the center of the string, I'm creating that node that you see somewhere right up there. Okay, so this behaves as a node, and the string is able to flex upwards over here, and it'll flex downwards over there, and they'll just resonate. And if you take a look at the difference between the two animations, the animation on the right is actually resonating at twice the rate compared to the left, and that will result in a change in frequency. Maybe you can tell the difference with your ears. You'll notice I'll be able to release my left hand from the guitar, and it'll still wobble at its second order of resonance. Yes, it is vibrating at double the frequency, which causes the sound to increase by a full octave. You can also take the same guitar string and break it up into thirds, like in the next animation. And the only way for this to resonate properly is for it to resonate 3 times as fast. All right, so I'll take the string and break it up into a third, and you'll find that this will, the perfect node will actually exist on the 7th fret. So this is a third of the full length of the string. So here's our reference note, and here's 3 times that frequency. If you have good relative pitch, you might notice that not only does it go by an octave, it also goes up by a perfect fifth. You hear that? And if I want this to resonate 4 times as fast, then I'll need to take this entire string and break it into small little quarters. And you'll notice that coincidentally, by the time you hit the 5th fret, this will be mathematically a quarter of the full length of the guitar string. 2 full octaves. So yes, the relative pitch difference between the 7th and 5th fret may be a 4th, but it's 2 full octaves from the original string itself. hope you have a better understanding of guitar physics now. And if you're wondering how in the world do I draw this in my notes, well, let me just give you the example of the first harmonic. Here are the two ends. Draw in two solid dots to indicate that this is a fixed end reflection. Here's the transmitted wave, and here's the reflected wave. And that's how you would draw it out by hand for a standing wave. One more time, there are some key important points on these waves over here. The part of the string that appears to be moving the most, that is known as the antinode. So you'll see that at the third harmonic, you form three antinodes. In fact, the antinodes tells you which harmonic you're at. And then when you take a look at your nodes, in this case over here, there are 4 nodes in total. 2 from the ends of the string, but you've also created 2 artificial nodes in the center, and that has to do with the fact that it's creating a standing wave. One last thing to emphasize about this is that the naming convention, it does get rather confusing. The first harmonic is always known as the fundamental frequency. But what's above the fundamental frequency? Well, you get the first overtone. But the first overtone is the same as the second harmonic. Similarly, when you upgrade from the first overtone to the second overtone, now you're on to the third harmonic. So just please watch out for the naming nomenclature. It is out of alignment between harmonics and overtones. There's a measurable distance between nodes, and you'll notice that measurable distance works out to only half a full wavelength. Alright, so the distance between 2 nodes will always be half a wavelength. So there is this formula. It's not an official one, but it is one nevertheless. dn is equal to 1/2 lambda times n. So in other words, how many consecutive nodes are there, and this will be the corresponding wavelengths between them. So for example, if you're going from here to here, you have 2 consecutive nodes. So if n equal to 2, 2 times 1/2 gives you a full lambda. And if you look at the animation, that is true. This is an entire full wavelength. Let's get through a few mathematical examples. Let's say we have a happy duck, and the happy duck bobs up and down in the water. Well, the water is not physically connected to the land itself, so the water is able to ripple up and down, forming an antinode between the water and the riverbank. However, in this case over here, the duck, as it's waddling up and down, it results in this standing wave of ripples. And the observer notices that the distance between nodes is 38 centimeters. All right, and the duck is bobbing, or sorry, the nature of the water itself is moving at 0.95 meters per second. So with these two numbers over here, what is the corresponding frequency of the duck? As this is a word problem, we always start off with our givens. So the distance between one set of nodes is equal to 38 centimeters. And the speed of the wave is at 0.95 meters per second. Once again, make sure you stick with MKS units. So D should really be written down as 0.38 meters. It just reduces any future accidental mistakes because you forgot to convert afterwards. Again, distance between one consecutive set of nodes is equal to 1/2 wavelength. So 0.38 meters is equal to 1/2 lambda. Therefore, lambda is equal to 0.76 meters. Lastly, we can use the universal wave equation, V equals F lambda, to solve for the frequency. So frequency is equal to speed divided by wavelength. So 0.95 meters per second divided by 0.76 meters should get you a frequency that's above 1 hertz. 0.95 divided by 0.76 gives you 1.25 hertz. Wonderful. Yay, everything works out. All right, last example, number 3. A standing wave has a distance of 45 centimeters between 4 consecutive nodes. So that adds up to 45 centimeters. What is the wavelength of the wave, and what is the corresponding speed? Now, as for the full wavelength, I think you could see that if you draw out the full physical picture. All right, this works out to 2/3 of 45 centimeters. So 45 times 2 is 90. 90 divided by 3 gives you 30. So it works out to 30 centimeters. That's quick and easy to figure out if you have a visual aid. However, without a visual aid, then you have to sit down and solve it mathematically. So once again, you start off with your givens. What do you know so far? You also know that there are 3 consecutive antinodes. So you're looking for d3 is equal to 1/2 lambda times 3, which will give you 3/2 lambda for d3. When you isolate for lambda, lambda is equal to 2/3 times your distance between 3 antinodes. So 2/3 of 45, or sorry, let's convert to meters. 0.45 meters will give you your 0.30 meters for your wavelength. There you go, the mathematical way towards getting to that answer. And for the last one, I hope you can answer it yourself. Speed is equal to frequency times wavelength. So since the frequency is given to you, multiply the wavelength by frequency, and then so they say, Bob's your uncle. There's the answer. That's how fast the wave is moving. For more fun adventures like this, go through your homework, and I'll catch you in the next episode. See ya.